In the stillness of Nevada's desert, something colossal is rising. Beneath the scorching sun and endless sky, steel, silicon, and ambition are reshaping the land. It's not just a rail line or a mine, it's an engineered rebirth. And by 2025, the most overlooked state in the West is becoming one of the most important. Gigafactory growth, Tesla's expansion in Sparks. 20 miles east of Reno Sparks, in the arid plains of northern Nevada, a titanic megaproject is transforming the landscape of manufacturing. This is Tesla's Gigafactory, a sprawling facility first conceived in 2014, now entering its next chapter with a $3.6 billion expansion, adding 4 million square feet of production space. At the core of this expansion lies the engineering challenge, to construct two new disciplines in one complex: a 100 gigawatt-hour, 4,680 cell battery plant, and Tesla's first high-volume semi-truck factory. The civil engineering of this expansion begins with massive groundwork. Steel frame superstructures now rise where once empty grading lay. According to local coverage in early 2025, exterior walls of the semi-facility were already completed, with the structural steel mainframe taking shape and getting ready to receive production line modules. Subsurface foundations have been engineered to carry enormous dynamic loads. Rolling gigapress installations, heavy automated conveyors, and overhead cranes for battery pack assembly. Inside, the mechanical engineering layout is equally formidable. The 4,680 cell factory requires precision climate control, Class 100 clean rooms, localized temperature and humidity conditioning, air filtration using HEPA modules, and dust control airlocks for electrode handling. High-pressure natural gas lines feed industrial HVAC systems for dry room dehumidification and process heating. These lines have been installed as part of the infrastructure planning from the outset. Electrical engineering is critical. The peak power demand for a 100 gigawatt hours per year lithium-ion cell plant is immense. Tesla's engineers are implementing high-voltage electrical distribution systems, medium-voltage switchgear, transformers, and redundant backup systems to supply continuous power to electrode coating lines, cell assembly robots, curing ovens, and test stations. On the semi-plant side, gigawatt-scale charging infrastructure must support factory QA and integration testing with substation transformers and industrial DC fast-charging rigs. Plumbing and utility engineering play a vital supporting role. The cell plant requires purified water systems, deionized water for coating, alkaline cleaning, and electrolyte formulation. Process piping distributes high-purity solvents and lithium-based electrolytes. Fire suppression sprinklers are installed throughout using hydraulic calculations to meet NFPA standards. Cooling water systems circulate through heat exchangers to maintain roller presses and battery pack assembly machines within narrow thermal tolerances. Automation and robotics define the internal choreography. Tesla's existing operations in Nevada already utilize high degrees of automation: bandolier wand loading of cylindrical cells, robots to transfer cells to assembly fixtures, and automated drive unit assembly with over 90% line automation. Now, the expansion intensifies that. New robotic gantries, machine vision inspection stations, and PLC-controlled conveyors are being integrated into both the battery and truck assembly lines. Project leadership for the expansion underscores the complexity. In mid-2023, Tesla hired Michael Hildebrand, a veteran capital projects executive, as head of Gigafactory Nevada, expansion engineering and construction, bringing decades of experience in multi-billion-dollar manufacturing programs. More recently, engineering leadership under Robert Jackson is steering growth engineering with a focus on innovative manufacturing solutions, sustainability, and efficiency. The supply chain overlay is also a feat of industrial logistics. Raw materials, lithium hydroxide, graphite, cathode powders will arrive by rail into the Tahoe Reno Industrial Center, offloaded into dedicated receiving areas. Inside, automated material handling systems route incoming materials into electrode prep lines and electrolyte mix rooms. Completion of the semi-production line is already underway. As of April 2025, Tesla has hired over 1,000 workers specifically for semi-manufacturing and begun setting up final assembly conveyors, quality control stations, and megacharger integration testing bays. The expectation is initial production by year-end 2025, with volume ramp through 2026 to tens of thousands of trucks annually. All told, the engineering of this expansion is a masterclass in integrated systems design, civil works, MEP infrastructure, automation, logistics, and sustainability. Features like solar and geothermal power feeding into a mega project intended to support both passenger EV and commercial EV battery production at unprecedented scale. The Silver Copper Crossing, the second bridge spanning the Colorado River between Laughlin, Nevada, and Bullhead City, Arizona. A 60.6 million, 724-foot-long precast concrete girder bridge. It rises 35 feet above the river, carrying 2 traffic lanes, with capacity to be restricted for 4, and a multi-use path for pedestrians and cyclists. Built by Fisher Sand and Gravel under Clark County Public Works oversight, the project also included a 3.5-mile approach road on the Nevada side and a 0.5-mile extension of Bullhead Parkway in Arizona, along with thoughtful environmental and aesthetic features such as a 2.5-acre habitat pond. The crossing is the first new bridge here in nearly 40 years and a vital infrastructure milestone. Constructed 8 miles south of Laughlin's original 1987 bridge, the Silver Copper Crossing spans a dynamic river environment subject to alluvial soils and variable scour conditions. The 35-foot deck elevation above the Colorado River reflects both hydraulic clearance and flood risk mitigation. Geotechnical specifics are not published, but the use of drilled shaft foundations, as reported, indicates the bridge's superstructure transfers loads through weak or unpredictable riverbed deposits into deeper strata. The multi-agency permitting process, spanning the U.S. Coast Guard Bureau of Reclamation, Fish and Wildlife Service, and state environmental departments, ensured the bridge did not impede navigation, wildlife corridors, or cultural resources. On-site, balancing river scour mitigation with foundation integrity likely required temporary cofferdams, casing techniques, and 3D site modeling to align shaft placements precisely, all standard in riverine bridge construction across federal waterways. The bridge employs precast concrete girder spans, a rapid and quality-controlled method well-suited for remote or constrained sites. Each segment likely consists of pre-stressed I or U girders supported on drilled shafts capped with a cast-in-place deck. The use of precast elements enabled simultaneous fabrication and site foundation construction, speeding deployment. A gracious 724-foot length divides into multiple typical spans, approximately 40 to 50 feet each, enabling manageable erection and efficient load distribution. Deck reinforcement and expansion joints reflect design considerations for thermal movement and heavy vehicle loading. One key engineering feature is the multi-use path, separated from vehicular lanes, structurally integrated through extended deck overhangs or segregated deck panels, and featuring overlooks for scenic views, adding both structural complexity and user value. The bridge's ability to be restriped from 2 to 4 traffic lanes illustrates design foresight for future traffic growth, requiring a moderately wide deck and structural capacity to handle increased loading, planned without additional support changes. The drilled shaft foundations were likely bored through river sediments and supported by temporary casing or slurry to maintain bore integrity. Rebar cages would have been lowered and shafts filled with tremie-placed concrete to avoid segregation underwater. After curing, pile caps tied the structure to the superstructure bearing supports. Approach works on the Nevada side involved cut-and-fill earthworks for the 3.5-mile connector to Needles Highway, requiring structural berms, pavement section design, compacted fill, and possibly retaining walls. On the Arizona side, the extension of Bullhead Parkway similarly involved excavation, embankment, paving, and integration with existing roadway networks, all coordinated to ensure grade match and proper drainage. Temporary cofferdams, diversion channels, and turbidity controls were almost certainly deployed during shaft drilling to protect river water quality and comply with environmental regulations, a key concern given proximity to wildlife and waterfowl habitats. The project's 2.5-acre nature center pond served both as mitigation and public amenity. While bridges typically lack complex MEP systems, Silver Copper Crossing includes structural lighting, trail lighting for the multi-use path, and possibly emergency call systems or surveillance infrastructure. Lighting design would focus on safety, durability, tamper-resistant, vandal-proof fixtures, and energy efficiency for nighttime use. Given the remote location, electrical feeds were likely extended via trenching along approach roadways, with transformers and switchgear housed in protective cabinets near bridge entries. Drainage systems, integrated grates and scuppers, manage deck runoff into engineered channels or retention basins to prevent scour and pollution. Any heating elements to address ice are unnecessary in this climate. However, expansion joint systems and waterproof membranes were critical to ensure deck longevity in the desert environment. Specific system specs were not published and are treated as engineering expectations rather than confirmed facts. Construction began in November 2021, with foundation drilling and casting followed by precast girder delivery and erection. The use of precast girder bridges accelerates schedule by allowing off-site fabrication concurrent with on-site preparations. Crews likely used barges or temporary trestles for placing girders, finishing deck pours, and installing railings and lighting. The 3.5-mile and 0.5-mile approach roads were graded and paved in parallel to bridge erection, ensuring access for heavy equipment and forming part of the same construction zone. Logistics included coordinating road closures, staged traffic diversions, and protected work zones across a multi-agency jurisdiction, requiring clear sequence planning to minimize disruptions. The project concluded with deck finishing, installing trail landscaping, approximately 1,400 bushes planted, and activating aesthetic and environmental features. Key risks included river navigation impacts, environmental approvals, foundation integrity in weak soils, and traffic disruption during construction. These were mitigated by extensive permitting coordination, environmental mitigation, aka Fay Nature Pond, and rapid construction methods. Sustainability was addressed through encouraging non-motorized mobility via the multi-use trail and habitat enhancement via the 2.5-acre pond and roadway planting. Structurally, precast construction reduces waste, improves quality, and shortens construction time, important in desert climates with limited work windows. The future-proof design allowing for restriping to 4 lanes adds flex capacity without structural modifications, a notable engineering strategy. The Athletics' new Las Vegas Ballpark rises where the Tropicana once stood, a sculptural domed stadium designed by Bjarke Ingels Group in collaboration with HNTB and being delivered by a Mortensen McCarthy construction joint venture. Planned capacity, approximately 33,000 seats. Planned opening for the 2028 MLB season. The project is being built on roughly 9 acres of Bally's 35-acre property on the Las Vegas Strip and is reported to carry a multi-billion-dollar price tag. Reported figures range from $1.5 billion to $1.75 billion. The team staged a ceremonial groundbreaking in June 2025. Heavy site and foundation work began earlier in spring 2025. This venue sits on reclaimed, heavily urbanized beachfront pass desert fill along the Strip, a compacted layered set of soils beneath reclaimed hotel foundations and the former Tropicana structures. Before vertical construction, extensive site clearance and demolition, including the October 2024 Tropicana implosion, removed legacy shallow foundations and underground utilities, but left a complex subsurface of fill, utilities, and pavement to contend with. Early construction activity documented in May, June 2025 shows caisson drills and deep foundation work underway, a clear sign that the design team is transferring stadium loads through weak shallow soils into deeper competent strata, using drilled shaft caisson foundations and large pads. Key geotechnical strategies expected on a 9-acre compact site like this. A. drilled caissons, bored shafts, to support concentrated column and bowl loads. B. Heavily reinforced raft slabs where appropriate to span variable fill. And C. Vibration and settlement management monitoring during pile installation to protect neighboring strip assets and subterranean utilities. These measures are industry standard on dense urban stadium sites and are consistent with the caisson rigs and early concrete pours reported on site. The stadium's visual signature is a series of overlapping shell-like pennant roofs and large glazing oriented toward Las Vegas Boulevard. The architects, BIG plus HNTB, describe a covered, climate-controlled ballpark with an expressionistic shell roof, not a full open bowl, designed to balance shade, comfort, and views of the Strip. The design calls for a fixed or covered roof concept with a very large cable net window facing the boulevard to create sightlines while limiting direct solar heat gain. From an engineering perspective, that roof concept implies long span girders or trusses spanning the bowl, a lightweight shell, potentially composite, or metal cladding over steel framing, and a cable net or tensioned membrane glazing system. The shell segmentation, aka the overlapping layers, helps break large spans into smaller, triangulated geometries. An efficient structural strategy that uses ribbed steel trusses and transfer members to avoid massive continuous cantilevers on a confined site. Engineering these shells requires 3D finite element modeling for membrane and plate action, dynamic load checks for wind uplift on the strip, and precise erection sequencing to keep the partially completed shells stable during construction. Site photos and trade reporting show large caisson drill rigs and early concrete pours, indicating drilled shaft foundations feeding into deep tamped or rock strata beneath the strip. Typical drilled shafts for stadiums of this scale are 3 to 8 meters diameter, depending on design loads, and are cased or slurry supported during drilling to maintain bore stability in loose fill. The construction manager, Mortensen McCarthy, has experience with large stadium foundations and complex logistics. They are likely sequencing work in zones so that the in-ground concrete cures while precast bent steel erection prepares the bowl. Mass concrete pours for a stadium bowl are executed in controlled lifts with thermal control plans like cement hydration tracking, cooling pipes, or staging concrete pours to avoid cracking. On a compressed schedule and high-temperature environment like Las Vegas, cooling blankets, mid-pour temperature monitoring, and stage-poured mass elements are standard. Expect post-tension slabs in concourses and spectator decks to provide long, column-free spans for sightlines and to reduce slab thickness and cracking risk. Las Vegas climate and strip environment drive critical MEP priorities: high-capacity HVAC, chilled water distribution, condenser plant sizing, and robust electrical redundancy. The ballpark is described as climate-controlled, with aggressive fan air conditioning strategies to maintain spectator comfort in extreme summer heat. Engineering such a system for a 33,000-seat covered stadium typically includes central chilled water plants with redundant chillers, multiple air handling units zoned by seating sectors, large rooftop or plant room condenser fields, and dedicated heat recovery loops for kitchen and hospitality loads. Given the scale, a central plant will likely be located in the stadium podium or adjacent hotel resort base, with medium voltage electrical service feeding multiple substations and distributed switchgear for lighting, concessions, and critical operations. Plumbing for concessions and hospitality will demand significant domestic hot water systems that's likely centralized with booster pumps, grease interceptors for concessions, and stormwater management that meets Clark County runoff requirements. Fire protection will be a mix of wet sprinkler systems in occupied areas and specialized high-capacity suppression for kitchen and mechanical rooms. Given the strip location, redundancy, surge protection for power, and EMI shielding for broadcast systems are engineering musts. Mortensen McCarthy's joint venture brings stadium-specific expertise and an integrated pre-construction approach, detailed scheduling, prefabrication of repetitive elements like precast seating risers, precast concourse panels, off-site MEP skids, and just-in-time deliveries to minimize on-site congestion on the 9-acre footprint. Reports show groundwork and early foundations beginning April to June 2025, and a ceremonial groundbreaking on June 23, 2025. The developer and team are targeting a 2028 opening, approximately 32 to 36 months of construction, meaning parallel work streams. Foundations and substructure, followed by steel erection and precast bowl assembly, simultaneous enclosure and MEP rough-ins, then fit-out and commissioning. On a tight urban schedule, crane logistics and staging are critical. Tower cranes will be positioned to avoid strip obstructions. Night shifts will manage concrete pours to reduce daytime traffic impacts, and strict vibration settlement monitoring will protect neighboring resort structures. Prefabrication and modular MEP skids reduce on-site labor density and speed commissioning. Principal risks. Cost escalation reports show estimates between $1.5 billion to $1.75 billion. Schedule slippage and utility coordination under a heavily trafficked strip corridor. Public funding and financing remain politically visible factors. Where figures vary, I flag them as reported, not as internal design facts. The team is mitigating risk through experienced CM selection, phased site work, and aggressive early procurement of long lead items like steel trusses, precast bowl pieces. On sustainability and innovation, design statements emphasize fan comfort and passive strategies, glazing orientation to limit solar gain, covered seating to reduce HVAC load, and efficient MEP central plants. The sculptural shell also allows daylighting where appropriate, reducing artificial lighting loads. These are design intents disclosed by the architects. Final energy modeling and commissioning reports, which would confirm predicted performance, are not yet public and should be treated as design goals rather than verified outcomes. Silver Desert Estates is a planned 282-unit, age-restricted affordable senior apartment community approved by the City of Las Vegas for a 15-acre site at Hickam Avenue and Jordanville Street in the Lone Mountain West Master Development area. The proposal calls for 7 2- to 3-story residential buildings and roughly 217,000 square feet of built area, designed to serve households at 60% and 80% of area median income. The city approved the rezoning and related variances in mid-2025, and developers have indicated construction could begin by late 2025. This project is framed as a targeted response to Las Vegas's growing senior housing deficit and will require tightly coordinated civil, structural, and MEP design to convert undeveloped master plan land into a compact, accessible living campus. The site lies inside the Lone Mountain West Master Development Plan, a planned community framework that prescribes land use, grading, street alignments, and stormwater controls for the valley's northwest quadrant. The master plan documents set the baseline rules for setbacks, drainage, and on-site open space requirements, meaning Silver Desert's civil design must conform to established grading and runoff corridors. The 15-acre parcel is currently undeveloped and subject to desert soils and alluvial deposits common to the region. Clark County and city engineering staff reviews for similar Lone Mountain projects routinely expect cut-and-fill balancing, compaction testing, and retaining walls to accommodate subtle topographic changes. Public meeting materials and the official city agenda identify typical geotechnical deliverables required for entitlements: a site-specific geotechnical investigation, foundation recommendations, pavement section design, and a stormwater management plan. For a low-rise residential layout on desert alluvium, geotechnical engineers commonly recommend shallow spread footings on engineered fill where competent native soils are near the surface, or isolated drilled shafts where deeper soft zones or groundwater concerns exist. At Silver Desert, the publicly available documents do not publish the geotech borings or R values, so all foundation specifics below are informed engineering expectations rather than confirmed design values. The master plan for Silver Desert Estates shows 7 buildings dispersed across the 15-acre footprint, with internal drives, centralized amenities, for example, leasing, wellness center, pool, and a generous outdoor circulation for accessibility. Low-rise, wood-framed construction is typical for 2 to 3-story affordable housing in Nevada. The plans submitted to the city indicate a stick-frame system over conventional shallow foundations, with Type FIV-A or 3A framing standards likely used to meet fire and sound separation requirements for senior housing. The lower building heights and repetitive floor plans allow cost-efficient platform framing with engineered floor trusses and prefabricated roof systems. Structurally, these buildings favor economy and speed, conventional spread footings or continuous footings under bearing walls, grade beams where slab-on-grade interfaces are needed for ADA access, and light-gauge steel or glulam for any longer spans in community rooms. Lateral load resistance will rely on shear walls like wood or light-gauge steel diaphragm action in the floors and josh roofs, and careful anchorage at the slab/foundation interface to handle seismic loads per Nevada code. The public documents don't release design calculations or member sizes. Where specific member sizing is discussed below, I label it as a standard engineering expectation rather than a published fact. The entitlement packet requires a grading and drainage plan that meets the Lone Mountain standards and Clark County runoff criteria. Construction will start with site stripping, removal of desert caliche and vegetation, followed by cut, fill balancing, and engineered fill placement in lifts with compaction testing. For 2 to 3-story wood frame structures on desert alluvium, the most cost-effective foundation is typically slab-on-grade with continuous strip footings. However, where borings reveal variable R values, designers often specify isolated pad footings or belled, compacted zones. The planning documents filed with the city require a geotechnical report and final soils recommendations prior to issuance of building permits. Stormwater will be addressed with on-site detention basins sized to a 100-year event per local code, plus LID measures for landscape irrigation and runoff quality. Utilities like water, sewer, reclaimed if available, will be extended from nearby mains. Coordination with regional sewer capacity studies and water meter availability is typically a critical path item for developments in the Lone Mountain area. Those utility capacity confirmations appear in later permitting stages and were not published in the public agenda documents we reviewed. For senior housing, EMET priorities focus on occupant comfort, redundancy, accessibility, and maintainability. Typical HVAC approaches for 2 to 3-story apartments in this climate include packaged rooftop units or split systems for individual units with a centralized plant for common areas like a fitness gym and a community room, combined with zoned, energy-efficient ventilation. Given Las Vegas's hot, dry climate, engineers emphasize sensible cooling capacity and dehumidification control for enclosed amenity spaces. Heat pumps with variable speed compressors are increasingly common for efficiency and serviceability. Electrical service will be sized to accommodate typical residential loads plus community services, including elevators if present, pool equipment, kitchen laundry, or life safety systems. Redundancy for life safety circuits, including fire alarm, emergency lighting, and accessible design for medical equipment, loads and units may be specified. Domestic hot water systems will likely use centralized boilers or high-efficiency tankless arrays with booster pumps and recirculation for rapid delivery to accessible fixtures. This is standard practice in multi-unit senior housing, but exact system selections and load calculations for Silver Desert Estates are not yet published. On a 15-acre site, construction sequencing allows simultaneous work streams, site grading and underground utilities, building pad preparation and foundations, followed by parallel framing of multiple buildings. Developers often maximize speed with repetitive building footprints, multiple crews framing identical plan sets, and with prefabricated elements like roof trusses, MEP skids for mechanical rooms, and pre-assembled bathroom pods if budget allows. Permitting timelines, off-site fabrication, and utility tie-ins will control the critical path. City meeting notes indicate the developer intends to move quickly toward construction in late 2025, subject to final permitting. Logistics considerations include on-site material laydown to avoid disrupting adjacent master plan streets, dust control in desert weather, and traffic management along Hickam and Jordanville during heavy truck movements. Night deliveries and stage paving are common mitigation tactics used on similar projects.